Welcome back to the show that tells you you are a quantum computer with free will that updates its model of the universe with every new measurement. My name is Justin Riddle, and this is episode 11 of the Quantum Consciousness series. Today, we will continue our discussion of epistemology. How do we know what we know? By talking about inference. In particular, we'll be talking about Bayesian inference and quantum Bayesianism. We will ask the question, do quantum computers update their theory or model of the universe through Bayesian learning? This podcast is available on YouTube, and an audio-only version is available on Apple Podcasts. If you find all this interesting, then please like the video, subscribe to the channel, leave a comment below, or write a review.
Join me deep inside the mystery of numbers. Come and huff a metaphysical new. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
All right, welcome back. So epistemology is the question of how do we come to know things about the world around us? How do we obtain knowledge and information? And it really is fascinating and sort of bewildering that we even know anything about the universe at all. So last week, we talked about deduction, and deduction fits squarely in the physical world because it conceptualizes everything as discrete variables that are either true or false. And then there's propositional logical statements to go from one set of true or false variables to another, and you can basically, through the process of deduction, figure out if new variables are true or false. And first-order logic is relevant to consciousness because digital computers are essentially first-order logical systems. So any limitations of first-order logic, i.e. Gödel's incompleteness theorem, also applies to digital computers. And the example in digital computers is known as the halting problem. So you can check out the previous episode, episode 10, about this topic, but in short, basically you cannot have a complete and consistent description through first-order logic that therefore describes first-order logic. So when you apply this to digital computers, you cannot describe the realm or the domain of digital computation using an algorithm within a digital computer. And so when we're trying to describe all of the universe in metaphysics, you're very much limited when you try to use first-order logic or digital computers because you're fundamentally going to fail in that endeavor. And so this really begs the question, what else is out there? What are some other forms of logical reasoning? And the obvious solution here, and probably why you're watching this video, is that quantum computers are here on the scene, and they're about to sort of expand the domain of how we think about models of consciousness. And so what is the sort of logic behind a quantum computer? And can that look more like a form of inference which fits closer to what human cognition is? And so today we'll be moving up to the mental world. And in the mental world, we'll be talking about inference or induction. And in particular, we'll be talking about Bayesian learning, quantum Bayesianism, discussing the Copenhagen interpretation, and then finally talking about how a quantum computer could maybe be some sort of Bayesian learning system. And as it sort of evolves into the future and makes measurements, it's collapsing the wave function, gaining new evidence, updating an internal model. And this could be some sort of model of how the mind works. All right, so to begin our discussion of inference and induction, I'm going to actually roll us back to something very fundamental in quantum mechanics. And so if you think back to episode 3, where we talked about the double-slit experiment, there was this idea that you're shooting individual particles at these two slits, and then the particle splits off into a superposition of going through both of the slits simultaneously, and then it gets measured at a far wall, and you see this interference pattern as it looks as if the particle is occupying a distributed wave function a probability space of multiple possibilities. And those probabilities are sort of interacting with each other, giving you this novel pattern on the far wall. But if you add a measuring device at one of the slits, and you actually sneak a peek at which of the slits the particle goes through, it chooses to go through the left slit or the right slit, and it removes that interference pattern at the far wall. And so I talked about how you're making this observation or this measurement at one of the slits. And in practice, this is some sort of atom or some physical matter there at the slit that when the particle or the photon or whatever it is comes towards that slit, it actually interacts with that particle that's sitting there, and that causes some sort of cascade chain reaction that you can then measure with your measuring device, and you can, gain the knowledge that it went through the left or the right slit. But fundamentally, it's the act of having a particle there which then changes the wave function. And so what gets very confusing in quantum mechanics, and I have very intentionally avoided bringing this up prior to now, but today we're going to dive into it, is this distinction between our knowledge about the double-slit experiment and then the reality of what the particle is actually doing. What gets very confusing about this is that if you try to say that the measuring device is like us observing the particle, then that knowledge is being extracted and you're learning about if the particle is in the left or the right slit, right? And so there's something called the Copenhagen interpretation. And this essentially tries to say that quantum mechanics is solely about our knowledge of these events. And so the superposition represents our uncertainty about whether or not the particle went through the left slit or the right slit. But that superposition doesn't really exist. It's actually a superposition of our knowledge about the particle that is in flux. Oh, I don't really know if it went through the left or the right. I have some probability it went through the left, some probability it went through the right. But the particle is actually just going through the left or through the right. And the superposition just represents our knowledge of the event. And so a lot of people that study quantum mechanics choose not to take the superposition seriously. They say instead, it's just our knowledge about the event. And then Schrodinger made a thought experiment to sort of poke at this resistance towards taking the event seriously. And this is called Schrodinger's cat. And so the idea here is you have a vial of poison, and there's a photon that comes at some measuring device, and it splits off into a wave function of traveling, let's say going to the left or going to the right. If it goes to the right, it hits this vial of poison and it releases the poison. But if the photon goes to the left, it just travels on and it doesn't touch the poison. And so when the photon hits the poison, it's going to release it and it's going to kill the cat. And if the cat, gets hit with the poison, then it dies. And so the question is, when the photon comes in, it goes into a superposition. That superposition is now the cat being alive if it goes to the left, or dead if it goes to the right and activates the poison. And so the cat is both alive and dead in superposition. And then you're the experimenter running this horrible experiment, and you now have a superposition of the cat being alive or dead until you peek in and look in the box if the cat is alive or dead. And then your friend is in the other room, and after you see that the cat is alive or dead, you shout over to your friend and you say, "Hey, the cat's dead." And then your friend, they had a superposition of the cat being alive and dead, and then they learn about it, and then it collapses their knowledge state into alive or dead. Now, this is all fun and games for the people doing the experiment, but for the cat is in an extreme predicament, right? It's both alive and dead simultaneously as the photon is in superposition. And so this question of knowledge is lost on the cat because the cat doesn't care what you think about the experiment or your friend in the other room. It cares about it being alive or dead. And so this thought experiment is meant to be ridiculous. It's meant to be preposterous. And it's meant to be impossible and kind of point out that the Copenhagen interpretation is fundamentally bizarre and doesn't really answer the fundamental question here of what is a superposition? Are superpositions real? And presumably they are very, very real. And so the alternative to viewing superpositions as some sort of knowledge state is that you have to take a superposition to be real on a metaphysical level. And so I think Roger Penrose really does this the best, but he says that a superposition is a blistering of fundamental space-time geometry, where you have the superposition or like one physical state, one space-time geometric configuration on the left, one on the right. These are two incompatible space-time geometries, and they both coexist. And furthermore, he says that there's a gravitational pull between the two different space-time geometries, and that these superpositions are fundamentally, inherently unstable, and they're trying to reconcile this blistering of reality and reconcile into just being one space-time geometric configuration. And that, his solution is that there's a gravitational pull between these different space-time geometries, and as the complexity of that wave function evolves, you reach some objective threshold, and then it collapses into being one space-time geometry, and that's, the one that really happens. In the many worlds interpretation, every superposition is real, but it's a multiverse, and they're like splitting off multiverses, and so it kind of takes the superposition to be real, but it just assumes there's just like a ton of physical universes. I personally find this very unsatisfying, and I prefer sort of the Penrose model of this gravitational pull between space-time geometries. However, the Copenhagen, the knowledge-based interpretation really doesn't like a universe blistering at this fundamental level. They prefer it to be a system that chooses one thing or another. We don't quite understand why it chooses one thing or another, but we make a measurement, and then our measurement has some probability associated with it. We can predict with some accuracy what thing is going to happen, and quantum mechanics is a way to figure out what we think about these events, right? We're like modeling the probability of events happening, but the superposition just represents our uncertainty. And so quantum Bayesianism, and I know I haven't introduced Bayesianism, but I'll do that in a second here. Quantum Bayesian is sort of an extension of probability theory trying to describe the world of quantum mechanics using this very Copenhagen style interpretation. And so the idea here is that there's wave functions, but we want to change these wave functions instead of viewing them as being these very bizarre new descriptions of reality. They're now being rewritten as probability distributions. And it's representing sort of the probability of this event happening or this other event happening, but it's sort of in a way a rejection of like that hard superposition belief where it's really splitting. And furthermore, when you talk about entanglement is this spooky action at a distance where two quantum systems, which were at one point in contact, now they're separated in space. And with simultaneous measurement, they seem to have correlated outcomes of those measurements despite this like spatial distance where there could be no direct information transfer, sort of a rejection of local reality. But in the quantum Bayesian model, the idea is that when you measure one thing or the other, you have knowledge about the other thing, but there is no direct contact between the things, right? So it's as if I gain near certain knowledge about some event occurring elsewhere, but that knowledge of the other event is not to suggest that this occurrence changed that distant event off, in that other location. So it's a rejection of that spooky action at a distance, underground entanglement webs and wires connecting systems beyond space and time, but that all that spookiness is really just a reflection of our knowledge, which is a lot less spooky, right? Because it's like, okay, I could have near perfect knowledge of some other event further away from me, but my knowledge of that here doesn't change the reality of that location, let's say on the other side of the planet. So if I know the sun is going to rise tomorrow morning on the other side of the globe, my knowledge that the sun is going to rise on the other side of the globe does not change the rising of the sun on the other side, right? Who am I to change the rising of the sun? All right, so I'm going to introduce Bayesianism now, just like normal Bayesianism, not quantum Bayesianism. And then we'll be returning to this idea of quantum computers as Bayesian systems. So Bayesianism is fundamentally a very simple set of mathematical principles in probability theory, which gives you a nice model for acquiring evidence and then updating your beliefs about the world. So very simply put, I have a set of beliefs about the world. These are my models, my different hypotheses or different theories. And these are called priors. And then for any given event that could happen, I have a likelihood that that event would happen given each of my theories. So for each theory, what's the chance that this event is going to happen if this theory is true? So those are my likelihoods. And then finally, after an event occurs, I have a posterior, which is essentially saying, now that this event has occurred, actually, how am I going to update my models and my theories based on this new evidence, which I now have? And so what this leads to, and you can kind of imagine this in like an artificial intelligence system, right? Where let's say you have some AI trying to play a video game and it's building models about the world around it. And then as events are happening, each of these different models or different like action plans of how to move around the world, each of those models is updated by the evidence. And then after you get that evidence, then you update your model, and then another scenario presents itself, and then you can update your model again. And you can kind of view this as interactive, where this agent, this like AI playing this game, it can perform actions, see the result of those actions, update its action plan, do another action, get the result, update the action plan. And you could also view it as a perceptual system. The world is changing. I have a model of what's going to happen next. Some new thing happens. I update my model about how I'm predicting the future of perception. So you can view it sort of as like an input-focused Bayesian learner or an output-focused Bayesian learning. Do an action, get a reward, get a punishment. See something, predict the next thing, get an error signal of how accurate your prediction was. And so Bayesianism gives you a way to sort of update or learn about the world through experience. And this is sort of the real key, interesting element of Bayesianism, is that there seems to be a sense of time, like naturally built into the Bayesian update, is this iterative process moving forward through time. And I think this is really the coolest, most interesting part of Bayesianism, is the flow of time. It's not time as a fourth dimension, meaning it can go forward or backwards. There is a single directional flow of time. New evidence comes in, you update your model, you keep moving forward. You're sort of ratcheting forward, learning about the world in a unidirectional motion of updating your models or updating your action plan. So I find that really fascinating because it really fits with our sense of time, you know? And so a lot of people are starting to view human cognition as a Bayesian learning process where you imagine a baby as a little scientist, and then it has predictions about what it's going to see next. It's moving, it's flopping its body around, and it's getting hurt or getting, some reward. And it's learning through experience how to, predict its vision, how to predict its perceptions, and how to update its action plans based on feedback from the world around it. And historically, to kind of contrast this against another theory, the frequentist is sort of the challenge to Bayesianism. And it sounds really funny because now we have all this, AI and stuff that uses these Bayesian update rules and these models of cognition that are pretty successful. And so it's kind of funny to imagine a world when Bayesianism came out, but it was actually a very controversial idea, Bayesianism, just at face value. And so to put you, in the center of that debate, the idea was you had the frequentists who said, I don't want to have a bunch of models or theories about the world. I want to know what the world is. And so I'm going to describe the world as it is. And I don't want to entertain all these weird theories with low probability. I want to collect data and say, this is true. And what does that sound like? It sounds like the first order logical framing. The frequentists tended to think more like these first order logical systems. They said, this is true, this is false. I want to collect data. I want to prove this. I want to prove that. And in a sense, that is how science works, right? We have ideas of this is true, this is false, this is how things work, this is how things don't work. But the Bayesian process is a little more true to the scientific method. I have theories about the world, and I update my theories based on evidence. That sounds like science. But then the frequentists want to say science is defined and fixed, and we've solved it. And so we have true, false values. The evidence came in, prove this, prove that, prove this, prove that. And they want to wrap it up with a nice bow and say, this is done, science is progressing, and here is the domain of human knowledge. But the downside is that it's a little dishonest to the scientific process of entertaining more theories. So the benefits of the Bayesian approach is that you're adding as many low probability theories as possible. And then as you come into evidence in the world, you then apply these evidence update rule to all your theories. And who knows, maybe these low probability theories actually start accumulating evidence. Let's say, for example, quantum consciousness was written off in your book. You were like, that's ridiculous and preposterous. I'm not even going to have a theory of quantum consciousness in my lexicon to even acquire evidence for it or against it. And so the Bayesian outlook on life would say, let's get as many different theories of consciousness as we can, and then let's just look at the evidence, update our theories, look at some more evidence, update our theories, and we'll just let the evidence talk, and we'll try to have as big of a basis set of theories as possible. And so I really love this Bayesian outlook because it sort of encourages you to have theories or have at least a basic level of respect for improbable theories. And then if the evidence doesn't support it, then they get, deranked. But if the evidence happens to support it, let's say quantum consciousness, you have some bias against it fundamentally just at face value based on some unknown, unsaid impression, then you never evaluate the evidence with respect to that theory, and it never had a chance to grow as a higher probability in your model space of theories of consciousness. Alrighty, so now that we've talked a little bit about Bayesianism, Let's bring it back to quantum Bayesianism or QBism, but then the people who made quantum Bayesianism call it cubism. Christopher Fuchs is really one of the core proponents of cubism. All right, so my understanding of cubism is it's viewing the world through this Copenhagen lens of here is a bunch of quantum systems and there's different probability distributions associated with the different outcomes of what could happen. And we're going to use principles of Bayesianism and probability theory to describe our knowledge of these quantum systems. And it's very Copenhagen in the sense that it's a lot to do with our knowledge of the events, our understanding of these quantum systems through a probabilistic lens. However, I will pitch to you right now a sort of, I don't know what to call it, a strong quantum Bayesianism approach. And I'm not sure if anyone out there really supports this or if it's just me theorizing on this, but here we go. So I'm going to harken back to this mind-body dualism, quantum digital duality, right? So the idea is that you have a quantum computer, it evolves, it gets measured, and then it goes into a digital computation phase. And then it evolves back into a quantum computation phase, it gets measured again, and the analogy here is that there's sort of this mind-body duality where you have a single unit processing all this information in the quantum phase, and then it becomes digitized, it gets all this sensory input, it gives all this action-oriented output, and then the cycle repeats. And so this idea of quantum Bayesianism would be that, or the strong quantum Bayesianism would be that this quantum computer is a Bayesian learner, okay? And the idea here is that when you go into the digital computation phase, you're acquiring evidence about the world around you, and you're also producing actions on the world. And then, based on that immediate feedback that you get, you update your priors, you update your model of the world, and when you evolve into that wave function quantum state again, you're sort of integrating this information that you've just received, and you're updating your models, you're updating your probability distribution, and then you're planning out your next predicted perception or predicted action plan. And then we go into the digital phase and we acquire evidence again. So one thing that quantum computers give us is it gives us a flow of time. So as the wave function evolves and gets collapsed, it's irreversible. You're moving forward. Every digital phase creates a irrevocable update in the system, and then it evolves from this new point. And so it has a unidirectional sense of time. And in the Bayesian model, you also have this unidirectional sense of time. And so the pitch here is that there's this one-to-one alignment between the Bayesian learning and this flow of time in the quantum computer where the update rule is being applied and then new evidence is acquired in the digital phase, and then this update rule is applied, and so on. And so there's a natural sort of alignment between these models, and this is definitely speculative, right? But this would be sort of a strong quantum Bayesian approach, where we're not talking about our knowledge as scientists about a wave function, but instead the wave function or quantum computer itself is the Bayesian learner, right? The quantum computer is a Bayesian learner. It is learning about the world around it. It's acquiring new evidence and updating its models. And so it's not our description of it, it's the thing itself as a Bayesian learner. All right. And then the final thing I want to mention is Heisenberg actions. So Werner Heisenberg had this idea that when you performed a measurement, you didn't just acquire information or measure a system, but you actually are acting upon the system. And so the measurement process is both an acquisition of information, kind of like a perceptual acquisition, but it's also an action upon the system. And so when I'm talking about measurement as like a perceptual thing, you're gaining new evidence. At the same time, measurements are actions. And so the lines are kind of blurred here. Acquiring information and performing an action is sort of intermingled in some way, or like it's difficult to pull these processes apart. And it might be that every time you acquire information, you're also performing some form of action as well. So then to put that back into the context of this Bayesian learning quantum computer, it is acting upon the world and acquiring information from the world, updating its models of how the world works and its action plans about what to do next. And then every collapse of the wave function is the acquisition of new evidence and acting upon the universe. And so this cyclical process of quantum computation, digital computation, is a generative, progressive evolution moving towards a better model of the universe and a better action plan for how to interact with the universe. And so if all of this is true, you're a quantum computer, you're learning about the world, and you're doing it through some sort of Bayesian update process as you grow your models. So anyways, next week we'll be talking about theories and, what is meaning? Is there a deeper meaning? But really, if I could give you a take-home message, it's try to be a little more Bayesian. Try to entertain theories about the universe, even if you think they're low probability. Just entertain them and allow the evidence to dismiss them. And sometimes you'll be surprised that the evidence will accumulate for those theories, which you had a very low prior on previously. Give it a slightly greater prior probability. Allow it to either accumulate evidence or become dismissed via a lack of evidence. So that's my take-home message for you. Looking forward to chatting again. Leave a comment, and I look forward to hearing what you have to say. Goodbye.